This is my 3 weeks of work for studying DirectX 12 and DXR. First of all, RTX on. Here I have implemented 2 rendering algorithms. First, photon mapping. Second, photon beam. Photon mapping is for describing the radiance on surface of the 3D models. This is the photon mapping result alone. And photon beam is for describing light due to participating media, volumetric participating media precisely. So what is volumetric participating media? It refers to objects with volumes and where light scatters or gets absorbed. Some examples of participating media are water, fog, fire, smoke and cloud, and also air, especially murky air. And the only participating media in this program is just plain air. You can see this murky air. So let me explain how photon mapping works first. I'm turning off photon beam again. So if I decrease the photon radius, I can see exactly where photon got hit. And I'm decreasing the number of samples for easier view. Yeah. These dots here are where photon got hit on the surface exactly. When you again back to the default image, turning off photon beam again, you can see that at this state, decreasing the number of sample photons decrease the quality of the image. You can also see the gaps between photons. This can be smoothed by increasing photon radius, which would decrease the details on image. So best image quality can be achieved when you decrease photon radius for more details and increase the number of photons. You can see the image quality becomes higher and FPS drops. High quality, low FPS, high FPS and low quality. Again, back to default image, and now I'm showing how photon beam works. So first decreasing the sample photon beams to 1. This is when there is only one photon beam. I'm turning off the light motion and light variation. So this is the near color. This is the color of the beam at the original light source, and distant color. This is the color of the beam at 1 unit distance away from the light source. Now the near color and distant color are really similar, so you cannot see any visible change, but if we change the distant color, you can see at some distance the color becomes the distant color, and at the original light source the light source original position, the color is the near color. So how does this affect actual image? Let's see this. Something brighter. Yeah, by adjusting this distant color, you can change the color of the participating media. Now, let's turn off the photon mapping. You can see the photon beam result alone, and by decreasing the beam radius, you can see exact path of the beams. So this is the exact path of the beam. Decreasing the number of samples for easier view. Now there is this air albedo parameter. This adjusts the ratio between light extinction and light scattering. So beam motion off. When you decrease air albedo, you can see that light extincts more, and when you increase air albedo, you can see that there are more scattering than extinction. Let's see how does this actually affect. Changing distant color. I'm changing distant color because at this state, when distant color is similar to near color, there isn't much light extinction or base light extinction or scattering. So changing color to increase scattering or extinction. Now, if I increase air albedo, there is more scattering. You can see that the air becomes more foggy. Decreasing air albedo, air becomes clearer, but more extinction of the light. There is more light extinction, but the image has become brighter. The reason for this is that there is increase in light power. To match the distant color and near color, the light power has increased as the albedo gets decreased. Less albedo means more light extinction, but you have to match this distant color with more light extinction, so there is increase in light power. You can see that increasing and decreasing albedo adjust the light power and other parameters. So with maximum scattering, I'd like to show one more parameter. Motion off, and photon mapping off. Beam radius decreased, decreasing the sample. So here is a parameter named Hanyei-Greenstein asymmetric factor. What this parameter does is adjusting the scattering direction of the light. So when this parameter is 0, the light scattering direction is uniformly distributed. light scatters to any direction uniformly. But when this becomes near to 1, light scatters to its original direction. Because this parameter also affects the visible light power, I'm showing the direct light hue. At 0, light just scatters at any random direction uniformly. At 1, it scatters near to the original direction. You can see the change here and there. For example, here. At 0, the light scatters at this direction, and when it becomes near to 1, it becomes straight as the light scatters near to the original direction. And when it becomes negative, light scatters near to the opposite direction. Yeah, you can see the change here. So how does this actually work in the actual image? Changing the light color again. Increasing scattering. And increasing Hg factor. Yeah, as if the value becomes near to the 1, it becomes less realistic, which is reasonable, because when you think of fog or water or any other participating media, you would expect that the light would spread to random direction, not just the direction slightly toward near to the original direction. When Hg asymmetric factor is exactly 1, their scattering direction is fixed. The light just keeps going without changing direction. So there is no randomness even if the value is exactly 1. Which is the same for the negative. When the value is negative 1, well, the light just scatters to the opposite direction without randomness. And yeah, negative also gives somewhat unrealistic result. So this is the result of changing Hg parameter at high albedo. Let's see the result at middle albedo. And at the lower albedo. Too bright. High Hg parameter somewhat gives somewhat like a crystal effect. More like areas are likely more like crystallized, I guess. This is more obvious when the light motion is off. albedo에 yeah, so that's all for the HEG. Now I've implemented these two algorithms with the Vulkan graphics library as well, but in Vulkan version I do not have a light motion or light variation. The Vulkan version is exactly like this. No light motion. Well, you can change camera views or camera position to get different radiance effect, but there isn't light motion. The reason why I didn't put light motion or light variation in Vulkan version was because I've had less understanding on RTX feature of the graphics driver ray tracing. in the Vulkan version, in DirectX version, in each frame I run two ray tracing pipeline, one for light simulation, the other one for actually drawing the image. But in Vulkan version, I only run the light simulation once, and for each frame they just use the same light simulation result to draw the image. But I got more experienced in the RTX and found a way to solve the problem in Vulkan, so I put light motion and light variation. So what is this light motion? Yeah, it's obvious, just light moving. You can change the absolute position of the light, which is here, and the light just moves around that position. Again, back to defaults. So what is this light variation? And this is turned off. There is light, but decreasing beam radiance. You can see that. Let's decrease the number of samples. Yeah, there is light moving, but the light is fixed direction. When the light variation is on, and I'm turning off the light motion off because the light variation effect is more obvious with light motion off. Yeah, you can see that the direction of the light changes as time goes. This light variation interval is the interval of this app to receive a new random seed. Basically, the app holds two random seeds always. It keeps two random seeds and receives new random seed at every interval of adjusted by this parameter. So when it receives a new random seed, it can read of the older one and make the result with the new random seed and the one that the random seed that it did not get written off. So basically there are two random seeds, and the result of two random seeds are the light direction or scattering and extinction length are linearly interpolated as the time goes. So when the new random seed is just received, only the first random seed is used to create the direction and light scattering and extinction. So say this interval is 10 seconds. At 10 seconds, when the interval begins, the new random seed does not have any effect, but when the time, like say 2 seconds has passed, then the result of the new random seed is multiplied by 20%, and the result of the older random seed multiplied by 80% to get the light direction and scattering and extinction length of the beam. So when the interval, when 9 seconds has passed from after receiving the new random seeds, then the result of the new random seed consists of 90% of the actual result, and the older random seed consists of the 10% of the result. So the result from consecutive random seeds are changing smoothly with this linear interpolation. And this is how this light variation is working. Now let's see the light variation interval, how the light variation interval actually changes the image. This is a 50-second interval, new random seed at every 50 seconds. About 4 seconds. About 1 second. 1 second. It somewhat gives a water-like effect. Which this may be natural if you're assuming that this thing is in the middle of water, but unnatural if you assume this thing is in the middle of air. So that's all for my portfolio. Thank you for watching my portfolio. There are references that I used for implementing this algorithm on my GitHub README page. So if you also have an interest in these two algorithms, you may check those references. Thank you for watching.